In this video, we're going to do our final example from the handout, example number 8. And again, it is another sort of mass gravimetric stoichiometry problem. But as you notice, they're basically all the same at this point. You just have to approach the problem with a balanced equation, and you should be good to go. So here we have example 8. An antacid tablet contains 0.5 grams of calcium carbonate and works according to the equation below. So A is determine the mass of hydrochloric acid that can be neutralized, and then B, determine the mass of calcium chloride that will be produced. So I'm going to do these in two different colors. I'll do this one in blue, and I'll do the next one in a different color. So we'll start off with A. First of all, let's make sure that there is a balanced equation. We have one calcium. Already I can see my chlorines are off. So if I put 2 here, that'll give me 2 chlorines, 2 hydrogens. Okay, 2 hydrogens, good. 3 oxygens, 1 carbon. I think we're balanced now. So it's a 1, 1, 1, 1 over here. And this is actually a neutralization reaction where we have hydrochloric acid and we have a base, a carbonate style base. And this is an antacid, so it will neutralize excess acid that comes up to your esophagus and might hurt it, like if you heartburn. So that's what an antacid is. It's a type of base that will help to neutralize any excess acid produced during the digestion process, and that might harm people when they're digesting or when they're eating food. So we have the mass of hydrochloric acid that can be neutralized. Okay, so essentially we're saying the antacid tablet, the mass of it, or the mass that it contains of calcium carbonate is 0.5 grams. And we want to know what mass of hydrochloric acid will react with it, what mass will be neutralized. So we're trying to find the mass of hydrochloric acid. So we have the mass of calcium carbonate, we need to find the mass of hydrochloric acid. The problem is we can't do a mass-to-mass ratio. You can't just take the mass of calcium carbonate and multiply it by 2 because it's a 1-to-2 ratio there. That's a molar ratio. So first we have to convert. Well, that's so step 1, making a balanced equation. Step 2, we have to convert the mass of calcium carbonate into moles of calcium carbonate. So CaCO3 is equal to the mass of calcium carbonate over the molar mass of calcium carbonate. And so we would get 0.5 grams over the molar mass of calcium carbonate. So let's go to our periodic table over here. Right here. So calcium carbonate has 1 calcium, so 40.08 plus 12.01 for the 1 carbon. And then there's 3 oxygens, so 48. So plus 48. And we get 100.9. So 100.9 grams per mole. 09 grams per mole, like that. And we're left with moles at the end. So we got 0.5 divided by that answer there. Then we get 0.0049955504. And that would be moles. Great, so we have that. And in this question, we're interested in the HCl. So we need to make a mole ratio between calcium carbonate and HCl. So we have 1 mole, or formula unit. And I say formula unit because it's really an ionic compound. So I should be saying formula unit if we have an ionic compound. So 1 formula unit or mole for every 2 moles of HCl present there. So that's how they're going to react in that 1-to-2 ratio. So if I had 1 mole of CaCO3, I should have 2 moles of HCl. And so in your head, you'd know already that we're just going to take the moles of CaCO3, multiply it by 2, and that gives us our HCl. So just another way to write this, by the way, you could also do 1 CaCO3 for every 2 HCl, or you could do for every 2 HCl that you have 1 CaCO3. So let's go ahead and show that now. We're going to show our last step. Well, one of our last steps, we're going to do the moles of calcium carbonate, 0.04995504 moles of CaCO3, and we're going to multiply it by one of these conversion factors that gets rid of CaCO3, and it's the one over here because CaCO3 is at the bottom. So 1 mole of CaCO3, and at the top we have 2 moles of HCl. We can cancel mole of CaCO3 out. Same thing over here. And we can do times 2 there, divided by 1, but it's the same thing. So we get 0.009991008 moles of HCl. So we found the moles of HCl. That's how many moles of HCl could be neutralized by 0.5 grams of CaCO3. So if you took that tablet, antacid tablet, you'd be able to neutralize that many moles of HCl with the antacid tablet. But the question's not asking for number of moles. The question's asking for mass. So now we can go and we can plug this mole into our equation here, into our formula there. So we have the mass of HCl that can be neutralized is equal to the moles of HCl that can be neutralized, and that comes from the previous step, step 3, multiplied by the molar mass of HCl. And so that's going to be the 0.009991008 moles times the molar mass of HCl. So that would be, what do we get? 35.45 plus 1.01. So that would be our 36.46 grams per mole. And so we can cross moles out, and we're left with grams in the end. So that would be 0.36427215 grams that can be neutralized. Now we do have to be careful. We have to make sure that we follow our Sig Fig rules. So let's take a look at our Sig Fig rules here. We said we have 0.5 grams. So we only really have one Sig Fig. So that's approximately, we're going to stop it here. That can round up to 0.4 grams. 0.4 grams of HCl that could be neutralized. So we could say that, therefore, 0.4 grams of HCl could be neutralized by 0.5 grams of calcium carbonate. All right, so that was part A. Now we're going to go ahead and try part B. So let's choose a different color here. Let's choose the green there. We're going to do part B in green. We're going to use the same equation, but we just want to figure out the mass of calcium chloride that can be produced from the 0.5 grams of CaCO3. So I'm just going to rewrite my equation here. And we're going to use some of the information we already used over there. So CaCO3 solid plus 2HCl AQ produces 1 CO2 plus 1 H2O. This is gas. This is liquid plus aqueous calcium chloride. Aqueous there. Okay. So in this situation, we want to find I believe the mass of calcium chloride produced. Is that what it was? Yes, the mass of calcium chloride that can be produced. So, and did we balance it properly? That was 1 over here. Okay, and 1 over here. So this is going to be, I think, a pretty straightforward one. So we want to find this mass, which is the moles times its molar mass. And the cool thing is, we actually already did a step here. We have the moles of calcium carbonate already. So we can use that. We found it over here. Where were we? Right here. So we can use that mole. In reality, if we didn't do that, we'd have to convert, but we can go ahead and use our mole ratio. So we know there's for every 1 calcium carbonate, you have 1 calcium chloride. And so because it's a 1-to-1 ratio, therefore, the number of moles of CaCO3 will be equal to the number of moles of calcium chloride, not the mass, but the number of moles. And that's going to be equal to the 0.004995504 moles. For a 1-to-1 ratio, it's acceptable to do that as long as you state it's a 1-to-1 ratio. You could always go and show your multiplication and cross things out. That would work too. But for 1-to-1 ratio, again, this is justifiable. And so we just want to find the mass that will be produced of CaCl2. So we have the moles of CaCl2. So now our last step is basically just to do the mass of CaCl2 is equal to the moles of CaCl2 times the molar mass of Cl2. And so we would get 0.0049955504 moles times the molar mass of CaCl2, which is, so calcium is 40.08 plus 35.45 for chlorine, plus another 35.45 for the other chlorine. So that's 110.98 grams per mole. We can cancel mole out, we get grams. So times our 0.00499 5504. And remember to use the unrounded number and then round at the very end. So we get 0.554401033 grams. And so what we want to do, though, is we want to make sure we're following the significant figure rules. So 1 sig fig there, which is what we had in the previous question as well, just to write that down. So we want 1 sig fig over here, 1 sig fig. And so we're going to have here, normally it's a 5, you want to round up over here. So we get approximately 0.6 grams of Cl2 that can be produced. So our step 4 is therefore approximately, so therefore statement, approximately 0.6 grams of CaCl2 will be produced. Now, I do want to challenge you, well, not challenge you, but I want you to check it out. You could have also used your HCl moles. Now, I recommend you just use the data provided in the question, just in case you made a mistake with finding the HCl, but it would have worked out. So just to walk you through it, you can try it yourself as well. You would have used the moles of HCl like this. You would have done, you had 0.009991. I'm just talking you through it here, 008. It's a 2-to-1 ratio between HCl and CaCl2. So you would have divided by 2 to find the CaCl2. And then afterwards, you would have multiplied by the molar mass. So you have the moles that multiplied by the molar mass, which was 110.98. And you would have had the same answer, 0.554401033. Because technically, if you did everything correctly, they're all going to react in their appropriate ratios. So you could have just used your HCl, use its ratio to CaCl2, and you would have had the same answer in the end as well. So you can try that out. See if you get the same answer. See if you know how to do the molarity practice. I just chose to go with the not molarity practice, mole stoichiometry practice. Molarity is something else we'll see later. I just chose to do the CaCO3 because it was given in the question and also was a nice 1-to-1 ratio, which was easy for me to do without some big complex calculation. So that was the end of the the questions in your handout, but you'll also notice if you scroll down, there's some extra practice problems in your handout as well. And the answer keys are provided on the link over here that you can click at. So just make sure you read the little tips over here and go through it. So you have these nice steps written out for you, and you can try using the steps to get your final answer and then check your work afterwards. So lots of practice over here for the different reactions. And really to get good at stoichiometry, you just need the practice. So do a bunch of these, go in your worksheets and choose a few that you haven't really seen much of before. Try them out. Take a look at your answers. If you don't get it right, well, don't stop the first time. Try again. Try to see why you didn't get it right and try to see until you get it right, where you went wrong so you can learn from those errors. It's the only way you're really going to get good at doing stoichiometry.